Welcome back to our mini-series on measurement-based quantum computation. Today it's the fourth part and it's on computational phases of quantum matter. So let's see what that is. And to put it a little bit into perspective, what have we done so far? First we talked about universality. Then we talked about fault tolerance. These are really indispensable parts. If we don't talk about universality and fault tolerance, then how can you even go further? Yeah, so this is absolutely necessary. So the third part was on quantum computation with probabilistic gates. This was motivated from an experimental point of view, because this is how you can make quantum computation efficient with photons. It's a very practical motivation. Okay, but what is the motivation for today? Today we have a theory motivation. Namely, we ask, what can we learn about measurement-based quantum computation from the perspective of symmetry? Okay, so what you have here is a stylized phase diagram of water. This is just to get you started on the subject. So, stylized phase diagram of water. Horizontal axis is temperature, left is low temperature, right is high temperature, up is low pressure, bottom is high pressure. So this gives us the liquid phase of water, and well, you can think about viscosity of water and stuff like that, but maybe that's not so interesting. Let's look at more complex properties. So we find that in this liquid phase of water we have life, and we have it nearly everywhere in the phase. It can be freezing cold almost, and at low pressure we have life there, and we have life at the very opposite. Bottom of the ocean, boiling hot water. There's life there too. Okay? Life everywhere, all around. Okay, but the liquid phase of water is not the phase that we are interested in, not the type of phase, and also we will be interested in a different property. Namely, what we'll be looking at are so-called symmetry-protected topological phases of matter. And the property we will be looking at is quantum computation, the ability to do measurement-based quantum computation. Okay, so this is our setting. So we are looking at Hamiltonians that have a certain symmetry. So there's a symmetry group, and the Hamiltonians of interest are invariant under this symmetry. And as the computational resource states, we consider the ground states of these Hamiltonians. Okay, and so what is a computational phase? So from the perspective of physics, a computational phase is a symmetry-protected topological phase, an SPT phase. So let's see what that is. So as you change your symmetric Hamiltonian, your symmetry alone won't fix it completely, so you can still change it. And as this happens, for every such Hamiltonian, you have a ground state and you have an energy gap above it. And as you move about in your parameter space, this ground state energy gap that will become bigger, or it will become smaller, bigger again, smaller again. And then occasionally it will shrink to zero. And let's look at such a point. Let's look at a level crossing. So while the ground states within such a phase, they vary only a tiny little bit from one to another. But when you run through a crossing, the ground states to the left and right, they suddenly change dramatically. So and that's why we associate the points where the energy gap closes with phase transitions. Yeah? And this now leads us directly to the definition of a symmetry-protected phase. So two ground states are in the same phase if there is a path between them such that at every point in the path we have a symmetry-respecting Hamiltonian, and the corresponding ground state, and for the Hamiltonian, along the path, the gap never closes. Okay, so let's summarize what computational phases of quantum matter are. Such phases are SPT phases. Now let's look at a particular state in such a phase. Say the cluster state is in one of such phases. Then for that state we already know what the computational power is, but the result is that the computational power is uniform across the phase. So for any state in that phase, the computational power is the same. All right, and this brings us to the outline for this lecture. So there's two parts. First, I will give you two motivations for why to look at this question. And then second, we go through 5 reference points, 5 important results in this field. Okay, so let's begin with the motivations. First motivation. So let's look at the night sky. Our version of the night sky is Hilbert space. So what we are interested in is all the resource states that exist for measurement-based quantum computation. And we wonder, what is their structure? Are these isolated states with no computational power around them, or are sets of useful resource states continuous, like what the Milky Way appears to be from a distance? Yeah, so that's what we want to inquire about. And there's 2 results in this regard. First result, universal resource state for measurement-based quantum computation exists. Yeah? So we have talked about in this series about the cluster state, and well, there's other states. There's, for example, the AKLT state after its inventors, Affleck, Kennedy, Lieb, and Tasaki. Yeah? Such states also exist in dimension 2, and when they have spin 3½ or spin 2, then these are also universal resource states. Yeah? So just to sum up, universal resource states exist. So the previous result was special instances, and now we have a general result. How frequent are NQCH resource states in Hilbert space? If we look at the volume of Hilbert space, then we find that only the tiniest fraction can potentially be useful. All the rest is guaranteed useless. And it's also interesting why this is so. And the reason is that all these other states are too entangled to be useful. Too entangled to be useful. Okay, so this is a general result that we have. And we may now ask, how is this affected by the presence of symmetry? Yeah? As was already mentioned, if symmetry is present, then resource states for NQCH are no longer rare, because now we have these extended phases where computational power is uniform. Yeah, so in those settings, computational power is no longer rare, but of course the symmetric setting by themselves are rare, and so there's no inconsistency with the previous result. Okay, so second motivation. And the second motivation is that we ask, can schemes of measurement-based quantum computation be described by symmetry in a similar way than, say, elementary particles can? Is there a classification of NQCH schemes by symmetry? And suppose we would know the answer to that question. Does symmetry have a bearing on quantum algorithms? Could we also classify quantum algorithms by symmetry? Yeah, so as you will see when we go through the results in this regard, about the first question we know quite a bit. We don't know everything, but we know quite a bit. About the second question, we know next to nothing. All right, so let us now talk about 5 important results that have been arrived at in this field. So here is the first one. It is by Akimasa Miyake, and he obtained it when he was a postdoc at Perimeter Institute. That's some time ago. The result is from around 2010, a little earlier than that. So what did Miyake consider? So he looked at a spin chain, bunch of spins in a chain, which are in the ground state of a Hamiltonian that has some symmetry. And now he was looking at quantum computation with this. And his scheme was a hybrid between measurement-based and adiabatic quantum computation. So the adiabatic part was that the respective ends of the spin chain, the qubits would be decoupled before the measurement. This decoupling would be adiabatic, and once decoupled, they would be measured, and that's the measurement part. For this scheme of computation, he found that the computation would work regardless of what the Hamiltonian was and regardless of what the ground state was. You didn't need to know these details. What guaranteed the proper computation was the symmetry. And the symmetry is all you needed to have. And Miyake immediately realized that this is connected to the phenomenon of symmetry-protected topological order. And so that's the birth of the field. Second result. So this is, phenomenologically speaking, both a step forward and a step backward. So the step forward is that this is now measurement-based quantum computation proper. There's no adiabatic part anymore. The step backward is that it's not about computation. It is only about transmission of information from the left end of a spin chain to the right end. And what the authors, and that's people from the group of Andrew Doherty and Stephen Bartlett in Sydney, what they showed was that this ability to perform quantum wire in a measurement-based fashion works throughout symmetry-protected topological phases. I mean, the protocol is the same, with the same efficiency, with any error lacking throughout the phase. Okay, I want to say a little bit more about the scheme. So what is really important about this work is the techniques that they use. So these are techniques of group cohomology. And in condensed matter physics, these techniques were already known. Condensed matter physicists have invented them, and Bartlett and Doherty and their group, they imported these tools from condensed matter physics into quantum computation. And that was a very important thing. So the DNA of group cohomology, they stuck in this field. So every paper, or not every, but nearly every paper subsequently builds on this knowledge, on group cohomology. Okay, so now we are going back to Miyake and his graduate student at the time, Jake Miller. And so this is very similar to the result that we saw at first. So this is a computational phase of quantum matter. This is measurement-based quantum computation in the presence of symmetry. Now it's without the adiabatic component. This is now measurement-based quantum computation only, and it is the first proof of a computationally universal phase. So 5 years after the term was coined, the first example was actually provided, and that comes in this paper. Okay, a result related to that. It is from my group, in fact, and it shows that the situation described by Miller and Miyake is not special, is rather a generic situation. You find many, many, many computational phases of quantum matter. And what is also important about this situation is that we have now a classification scheme. So there is this group cohomology data that I didn't explain, didn't even touch upon, but sure, it is the group and then something that's called the group co-cycle. It's a cohomological structure. And these two things, the symmetry group and the group co-cycle, it turns out they describe symmetry-protected topological phases in one dimension. And that's what the condensed matter physicists had figured out. Okay, and this can now be applied to quantum computation, measurement-based quantum computation. And so we have the SPT to MBQC meat grinder. And what it does is it takes this information, this cohomological information regarding the symmetry group, you grind that through the meat grinder, and out comes a scheme of measurement-based quantum computation that is complete with the gates that you can simulate and the observables that you can measure. Okay, let's take a break here and do a little inspection. So everything that I have shown you so far is on one-dimensional systems, spin chains, and from the point of phenomenology, this is not so interesting. You cannot have universal quantum computation that way. And I want to show you why this is. Okay, and well, the fact is simply that when you translate measurement-based quantum computation to the circuit model, which is what you would do for the universality proof, then you lose one dimension. So a two-dimensional cluster state becomes the circuit model operating on a linear register, and the one-dimensional cluster state becomes a quantum register that's just a point. So you end up with a finite number of qubits. And with a finite number and bounded number of qubits, you cannot have universal quantum computation. And therefore, to reach universality, you need to go to higher dimension. And that is the last example that we're going to look at. Okay, so let's look at this final piece of work here. So this is in 2 dimensions and it describes a computational phase that is universal. So let's look at the setting. We are embedding the phase on a torus. This is just because of our laziness. Yeah, we don't want to deal with boundary conditions because boundary conditions are sometimes tricky. And then locally, the lattice looks like what you see here. Yeah, it's a simply square lattice. But what's interesting is how the symmetries act. So in 2 dimensions, we are dealing with what's called subsystem symmetry. So in this case, the symmetry acts differently on different qubits. Yeah, what's shown here are 2 generators of the symmetry, and both act in a diagonal fashion. So only the qubits on a line are acted on non-trivially, and the other qubits are acted on trivially. Yeah? So these are 2 generators, and all the translates of these generators are also generators. This is how you get the symmetry group. Yeah? So that is how the symmetry acts. And well, we observe that the 2-dimensional cluster state exactly has this symmetry. So there is a phase under that symmetry that the 2D cluster state is part of. And this is the phase that we are considering. And for this phase, we can say, and this is now the main result, that all states in it, all ground states in it, except maybe a set of measure 0, all of these states are resources for universal measurement-based quantum computation. Okay, so that was our first universal quantum computational phase. So now I would like to explain to you a little bit how this result is derived. I do not have the time to give you the full proof. I just want to give you an idea, and I want to make you a little bit curious about the thoughts and the ideas and the concepts that are involved in this proof. So it begins right here. So what you see here is the resource state. That could be the cluster state, 2D cluster state, or some deformation of it. You see it described as a tensor network. So every yellow block is a tensor. It has a physical leg coming out of it. That's the red leg, and each of them represents a single particle. And then you have these other 4 legs coming out, and they are called virtual, and they are contracted over. And this is how the quantum state is produced from those tensors. And so the good thing about this description is that you can describe an entangled, very large state just by these individual tensors. So the tensor is the building block of the state, and all the properties of the state must derive from this single block. So any such single block is what we will now be looking at. Okay, and these blocks have certain properties irrespective of which state in the phase they describe. Namely, they have particular symmetries. So we can say that any state in the phase can be described by a tensor with the following symmetries. So you see the symmetries in this upper line with a bunch of examples, bunch of symmetry generators. So you see a couple of Pauli operators coming in, acting on these legs of the tensor, both the physical and also the virtual legs. And well, the tensor is invariant under the application of those combinations of Pauli operators. So that's what's shown in the upper line. So this defines the symmetry group. Okay, so what does this have to do with cluster? So it turns out that if to those four symmetries we add another one, another symmetry generator, that's the one shown below, if you have this one additional symmetry, then it turns out that the only solution that you have left for the state resulting from those tensors is the cluster state. Yeah, but here we are not talking about cluster states only, we are talking about a phase, and it turns out for every state in our SPT phase, the upper four symmetries hold. Not the fifth, but the upper four. And that's why we call these states cluster-like. Yeah? And now, with these symmetries, you can do funny things. So the entire computation is reasoned with the help of these symmetries. So what you see here is the very simplest logical operation, the identity gate. So there's many computational scenarios in which the identity does itself. You don't need to do anything about it, but here it's a little bit different. So the identity gate is a fairly complicated song and dance. So let me describe this to you. So what you see here, say on the left panel, is a combination of symmetries. And the symmetries are chosen such that if you have neighboring tensors, then of the left tensor, the right outgoing leg, and of the right tensor, the left outgoing leg, they must match as far as their symmetry content is concerned. Yeah, so edges match. This is how we are composing the symmetries. And so then we have legs sticking out to the left and the right. Yeah, so on these vertical virtual legs, we have our quantum register located, and we see that an incoming Pauli operator sigma z after this complicated long song and dance becomes a sigma z again. And likewise for the sigma x on the virtual quantum register, after this long song and dance, it becomes a sigma x. We have translation invariance, so we have all the translated copies of that as well. And so we see every z is mapped to itself, every x is mapped to itself, and that is what the identity operation does. So this is an explanation of the identity gate in terms of symmetry. Of course, identities is a little bit boring, so you want to do the other gates as well. You want to do a universal set of gates, and it turns out that the explanation of these gates can also be done in terms of these symmetries. So what you see here on this slide is how you do an entangling gate. So it will be exponential of xzx, and that is something you can implement by measuring a qubit somewhere in the bulk in a basis rotated away from the x eigenbasis. And as we know it in measurement-based quantum computation, the measurement angle, so let's repeat something from an earlier lecture. So the measurement angle will be related to the rotation angle. Okay, so this is how you do an entangling gate of the form given. If you do this off x-axis measurement on other locations, you implement different gates. So you can implement local x rotations and local Z rotations, as is shown. And it turns out that these three types of gates here form a universal set. And so this is how you explain universal quantum computation in this fashion, using the symmetries. Of course, the argument, if you really do it, is much, much longer. I just want to give you a gist of it and make you curious. Okay, so that was the fifth piece of work, and that brings us to the end of this lecture. So let me summarize what we talked about. I mean, we haven't really proven anything here today. The proofs are long that are hiding behind, but let me just say what we did. We talked about a classification of MBQC schemes. Remember our motivations. This is what we wanted. Unfortunately, the classification we have obtained holds in spatial dimension 1 only, and phenomenologically, as I told you, dimension 1 is not as interesting as the higher dimensions because you need to go to higher dimensions for universality. And that was the second thing. In higher dimensions, specifically in dimension 2, we found a computationally universal phase. So these are the two results that I wanted to alert you to today. Thank you very much for your attention. This ends today's lecture, and this also ends this mini-series. So let me say a few concluding remarks about the mini-series as a whole. So you have learned quite a bit about measurement-based quantum computation. We talked a tiny bit about experiment. Well, you learned, maybe most importantly, about universality of the scheme and how to prove it. You learned about fault tolerance. Okay? There's also a rather large number of things that we didn't talk about because there was not enough time. So I want to recommend to you to look up, if you are interested, in particular two things. So these are the connection between measurement-based quantum computation and contextuality, and the connection to graph theory. And that concerns the concept of local complementation and concepts like tree width and rank width. And I have prepared for you a few references. So the first two references are the graph theory part, and the second set of two references is the contextuality part. So dig it out if you're interested. Thank you very much for coming to this mini-series.